Hey everyone, welcome back to our data structure tutorial series. In last video, we have covered several operations on array data structures. In today, we are diving deep into something that fundamental yet often overlooked. The memory representation of arrays. If you have ever wondered how arrays are actually stored in your computer memory and why it is matters, then stick around. We are about to uncover the magic behind arrays that make them so fast and sometimes tricky to work with. Now, let's take an use case. Let's suppose you are building a game app with labels, characters, and scores. You decided to store all players' scores in an array. It worked perfectly at first, but as game grows, things started to get slow. You scratching your head and wondering why it is happening. The arrays worked fine before. The answer is memory. The way arrays are stored and accessed in memory can make or break the performance of your application. So, today we break it down step by step. So, what exactly do we mean by memory representation? Think of your computer's memory as a huge bookshelf. Every slot on this shelf has an address, just like a book's location in library. Now, when you create an array, you are essentially reserving a section of that bookshelf, all neatly arranged next to each others. In technical terms, arrays are stored in contiguous memory locations, which means all elements sit next to each other, like books on the shelf. This is what makes accessing elements in an array is so fast. But there is more of it, and that's what we will explore next. Why does contiguous memory matters? Well, when you want to access an element in an array, you just need to know the memory address of the first element. Let's call it as a base address. And the position of the element you want, its index. With this simple formula, the computer can jump directly to the memory location of element you need without searching throughout entire array. Now let's take an example. Imagine you have this array of integers like 10, 20, 30 and 40. Each integer is stored in memory location that's 4 bytes wide. So if the first element is stored at memory address of 1000, the second element will be stored at address 1004 and third at 1008 and so on. Now, when you ask for the element at index 2, the computer calculates the memory location. Base address, that is 1000, plus index 2 multiplied by element size, that is 4, equal to 1008. 1008 is address of 30. You can directly access the value 30. It will not take any time. Alright, what about multidimensional arrays like 2D arrays? Think of these as arrays within arrays, like rows and columns in a table. But even though it looks like a grid, it is still stored linearly in memory. The two most common way to store 2D arrays in memory. Number 1, row measure order, where rows are stored one after other. Number 2, column measure order, where columns are stored one after other. Most programming languages, including C and Java, uses row measure order, which means the first row is stored entirely before next row begins. But there is a catch. Since arrays occupies contiguous memory, If you need to expand an array, the computer might not find enough free space right next to your existing array. In that case, it has to move entire array to new memory location, which can be costly in terms of time. That is why dynamically growing arrays like JavaScript arrays or Python list sometimes takes a performance hit when they grow beyond the initial size. Behind the scenes, they copy data to new chunk of memory. So, why does any of this matter for you? Well, understanding how arrays are stored in memory can help you optimize your code. Whether you are building a game or any algorithms or just trying to make your app run faster, knowing how data represented can give you that edge. Let's quickly recap what we learned so far. Arrays are stored in contiguous memory locations. This allows for super fast access to any element using a simple formula. In 2D arrays, data is stored entirely in row measure or column measure order. And finally, expanding array can lead to a performance bottlenecks due to memory relocations. In our next video, we are going to dive into application of array. Thanks for joining me today. If you found this video helpful, hit that like button and don't forget to subscribe so you won't miss next episode in our data structure tutorial series. Until next time, happy coding.